Welcome to the Regents Physics Circular Motion and Gravity problem set, problems numbers 5 and 6. Number 5, a coin is placed on a vinyl stereo record making 33 1/3 revolutions per minute. A, in what direction is the acceleration of the coin? B, what force accelerates it? And C, in which of the three radii listed in part B would the coin be most likely to fly off? Explain. Let's start with a diagram of what's going on in this question. Here we have our vinyl record, and on it we'll place our coin here on the edge to start with. In what direction is the acceleration of the coin? Well, using an arrow, we'll label the acceleration of the coin, since it's traveling in a circular path, to be towards the center of the circular path. Next, what force accelerates the coin? Well, we start off with sigma F equals ma. Is the coin accelerating? Yes, because it's traveling in a circular path. So we add a subscript C to our A value, telling us that it's centripetally accelerating. Next, let's do a free body diagram showing the forces acting on the coin. Here's the coin side view. Here it is top view. Here it is side view. What forces are acting on the coin? We have its weight down. We have the record pushing back up against the coin with the normal force, Fn. And we have the static friction pointed in this direction, keeping the coin from sliding off the record. So we can see that the force keeping the coin on the record, and the only force supplying the centripetal acceleration, is the static friction. So Fs equals mv squared over r. So the answer to B is the static friction between the coin and the record. C, in which of the three radii listed in part B would the coin be most likely to fly off? Explain. Difficult question to answer because there were no radii listed in part B. So let me help you out here. We'll let this radius be one of the three radii, and we'll just put the coin at two different other spots. Let's suppose we put it here, kind of in the middle of the vinyl part, and let's put it here, kind of on the very edge where the center of the record is. Okay, we'll move this one out a little bit. There we go. Three different radii here. Okay, so which of the three radii would the coin be most likely to fly off? All right, here we go. So to analyze this, we have to analyze what things remain constant and what things don't. And what things are changing in this equation. You may recall from our study of friction that friction is calculated by mu s normal force. Extending that one more, the normal force for this object, since it lies on a horizontal flat surface, is equal to and opposite its weight. So instead of mu s, we can write mu s mg. Well, let's take a look. The issue here is that there's going to be a limit of friction. The static coefficient's not going to change in these three spots. The molecular interaction between the coin itself and the vinyl is not going to change. So mu s is constant, little g is constant. What that says is that there's a limit to the amount of static friction that will keep the coin traveling in a circular path. This value on the left side can't change. So, if we decrease the radius, what does that mean? Decreasing the radius increases, inverse relationship, increases the amount of friction that would be required to have the coin traveling around the circular path at the same speed. Well, the record continues to make 33 1/3 revolutions per minute. And while the radius is changing, okay, and that will change the speed. Notice that the speed here is squared. So the thing that's going to make a bigger impact is the speed here, along with the radius of the circular path. So as you get closer towards the center of the circle, as you decrease the radius, more friction would be required. So the coin where it would be most likely to start sliding and fly off would be the coin towards the center, the smallest of the three radii. Okay? All right, number 6. According to the Guinness Book of World Records in 1990, the highest rotary speed ever attained was 2,010 meters per second, which is 4,500 miles per hour. The rotating rod was 15.3 centimeters, which is about 6 inches long. Assume the speed quoted is that of the end of the rod. A. What is the centripetal acceleration at the end of the rod? And B, if you were to attach a 1 kilogram object to the end of the rod, what force would be needed to hold it on the rod? We start with A. The formula for centripetal acceleration is A equals V squared over R. They told us the velocity was 2,010 meters per second, and the radius was 0.153 meters. Make sure to convert that from centimeters to meters to be consistent with your velocity units. Don't forget to square when you do your calculation. And when you go ahead and do that, you should get 2.64 times 10 to the 7th meters per second squared to 3 digits. We now take that, the force required would be the centripetal force necessary to keep it traveling in a circle. And so F equals ma, c. And we were told the object was 1 kilogram that you would attach, and we've already calculated the acceleration. So the numerical value of our force ends up being the same because we're simply multiplying by 1. And so we get 2.64 times 10 to the 7th newtons. That is a lot of force. All right, more to come with circular motion as we do another practice problem in class tomorrow, number 7.